There's something happening right now that should terrify us, or maybe it should excite us. Honestly, I'm not sure which one is the right response anymore. We're living through two of the biggest technological revolutions in human history at the exact same time. And they're starting to collide. One revolution is artificial intelligence, which has been accelerating beyond almost anyone's predictions. Just 5 years ago, experts thought we were still decades away from language models that could write coherently and pass college exams. Now we're past that point by so much that the question isn't whether AI can write or think or reason. It's what can't it do? What are the limits? The other revolution is quantum computing, a technology so fundamentally different from everything we've built that most people don't even know it exists yet. It's not like the jump from computers to smartphones. That was faster processing and better interfaces. It's more like the jump from mechanics to electronics. It's a different paradigm altogether, a different way of processing information at the most fundamental level. But here's the thing that keeps scientists up at night. What happens when you combine them? What happens when you take the most powerful computational tool we've ever created and supercharge it with quantum mechanics? What happens when you feed quantum processing into neural networks? The answer might be something that changes everything. Not just technology, not just society, but the very nature of intelligence itself. And more importantly, the very nature of what we're capable of understanding and controlling. The perfect storm is forming because these two revolutions are arriving simultaneously, and they're amplifying each other in ways that are hard to predict. For decades, artificial intelligence was progressing steadily but slowly. We built systems that could play chess in the 1990s, then recognize images in the 2000s, then have conversations in the 2010s. Each milestone took years of work. Deep Blue beating Kasparov took a decade of research. ImageNet recognition improvements took a decade. Deep learning itself took 15 years of incremental advances before it suddenly mattered. Each breakthrough required new algorithms, new data, new architectures, and most importantly, people willing to fund research that seemed frivolous at the time. But then something shifted. Around 2016, 2017, the pace started accelerating. Neural networks got deeper and more efficient. Data became more abundant as the internet grew and sensors proliferated. Computing power grew exponentially and kept doing so even as Moore's law slowed. And then came large language models, systems like GPT that could suddenly do things we didn't think were possible. They could write essays that read like a human wrote them. They could code in multiple programming languages. They could reason through complex problems and explain their thinking. They could engage in philosophical debates. For a moment, it felt like we'd cracked something fundamental about intelligence itself. Maybe the theory said that sufficient scale and sufficient data could produce something that approximates understanding. Maybe raw pattern matching was all intelligence ever was. But AI researchers know the truth underneath that enthusiasm. Current AI is running on classical computers, machines that process information using bits that are either 0 or 1, yes or no, true or false, on or off. Every operation, no matter how complex it looks on the surface, is just billions of simple binary operations stacked on top of each other. And we're starting to hit limits with this architecture. The models keep getting bigger, sure, but the gains are slowing down. You need more and more data, more and more computation to get smaller and smaller improvements. It's like climbing a mountain where the air gets thinner and thinner the higher you go, and your lungs work harder for every step. We can keep climbing, but at some point, something fundamental has to change. The energy costs are becoming astronomical. Training GPT-4 reportedly consumed electricity equivalent to powering a city. The data requirements are reaching the point where we're running out of high-quality text to train on. The model performance improvements are diminishing. You're spending 10 times the compute for single-digit percentage improvements. That's not sustainable. That's not scalable. That's the current classical AI hitting a wall. And that's where quantum computing enters the picture. like a key that might unlock something we're not ready to handle. For the last 50 years, quantum computing was mostly theoretical. It lived in research papers and university labs where physicists debated whether it would ever be practical. The idea was seductive, though, which is probably why people kept working on it despite the engineering nightmares. Instead of bits, quantum computers use qubits, which can be 0 and 1 at the same time through a property called superposition. This means a quantum computer could, in theory, explore vastly more possibilities simultaneously than any classical computer. If you have 3 classical bits, you can represent one of 8 possible combinations at a time. The bit configuration might be 101, or 011, or 000, but it's always exactly one of those 8 options. But 3 qubits can represent all 8 combinations simultaneously in superposition. Add more qubits, and the advantage doesn't just grow, it explodes exponentially. Exponential. That word should make you pay attention. 4 classical bits can represent 16 combinations. 4 qubits can represent all 16 simultaneously. By the time you get to 30 qubits, you're talking about over 1 billion simultaneous states. By 50 qubits, a quadrillion. By 300 qubits, you're dealing with more simultaneous states than there are atoms in the observable universe. A number so large it's meaningless to compare it to anything physical. That's the theoretical promise of quantum computing. But there's a catch. Actually, there are many catches. Several catches stacked on top of each other like Russian nesting dolls of engineering problems. Qubits are incredibly fragile, more fragile than anything we've ever tried to build. They need to be isolated from heat, and I mean almost absolute 0 temperatures. They need to be isolated from electromagnetic radiation, which is everywhere. They need to be isolated from vibration, from sound waves, from air molecules bouncing around. The slightest interference causes what's called decoherence, which means the quantum state collapses and your computation falls apart. It's like trying to write a message on water. The moment you're done, it vanishes. Building a quantum computer is like trying to choreograph a dance inside a minefield while wearing a thick suit of armor and being only able to see through a small window. Every dancer has to move perfectly in sync. Every step has to be precise, and the slightest stumble ruins everything. That's why we're still in the early stages. The most advanced quantum computers today have maybe a few hundred physical qubits, and they can only maintain their quantum states for microseconds to milliseconds. Actually, let me be more precise. The quantum coherence time is often in the hundreds of nanoseconds range for the best systems. That's billionths of a second. In that tiny window of time, the quantum computer has to perform its calculation, find its answer, and measure the result before decoherence destroys everything. It's progress, yes, but we're nowhere near the thousands or millions of logical qubits we'd need for truly world-changing computation. We're nowhere near error-corrected quantum computers that can run long, complex algorithms. So why is everyone talking about the danger? Why does it feel like we're on the edge of something apocalyptic when the technology is still so primitive? The answer is that people have been predicting technological apocalypse for a very long time. It's almost a tradition at this point, like a cultural constant. Every generation has its doomsday technology. In the 1950s, people thought computers would cause mass unemployment and societal collapse. The machines would think faster than humans, so humans would become unnecessary. They didn't become unnecessary, though computers did transform the job market in ways nobody expected. Some jobs vanished, sure, but new jobs were created. Entirely new categories of work emerged that nobody could have predicted. In the 1970s and 1980s, there were predictions that automation would make most jobs obsolete. The robots are coming to take your jobs was the constant refrain from both optimists and pessimists. Factory automation did eliminate millions of manufacturing jobs, but the labor force adapted. People retrained. New sectors grew. And while automation has eliminated certain types of work, it also created entire new industries. The internet was going to destroy privacy and create dystopian surveillance states. Well, that one's more complicated. The internet did create massive privacy concerns and enabled surveillance in ways that would have seemed science fictional in 1990. But it also connected humanity in ways that have been genuinely beneficial. It democratized information. It enabled communication across borders. People found community in ways that would have been impossible before. Nuclear power was supposed to be either the salvation of humanity, providing unlimited clean energy, or its doom-destroying civilization through accidents and weapons. It ended up being something much more mundane, just one energy source among many with its own trade-offs and its own ongoing debates about safety and waste disposal. Genetic engineering was going to create designer babies and a genetic aristocracy, splitting humanity into modified and unmodified classes. We got Dolly the sheep instead, and we're still having the same ethical debates we were having in 1973. The doomsday never arrived. The apocalypse kept not happening. The point is that technological apocalypse predictions have a terrible track record for accuracy. They're almost always too extreme and too dramatic. They assume technologies will work the way theoretically possible, rather than the way they actually get implemented in a messy, complicated real-world context. They underestimate human adaptability and overestimate the speed of technological deployment. They assume Moore's law will continue forever when it's already slowing. They assume engineering problems will be trivial when they're often the hardest part. So when people start talking about quantum AI causing the end of civilization, you might be forgiven for rolling your eyes. Based on history, it probably won't happen. The apocalypse probably won't arrive on schedule. We'll muddle through like we always do. But, and this is a big but, maybe the thing that makes this time different is that we can actually see the mathematics. We're not guessing about what quantum computers might do. We can do the calculations. We can see the theoretical speed-ups. We can look at the algorithms and understand why they work. That's different from past predictions. But this time might actually be different, and here's why. Previous technological revolutions happened sequentially, giving society time to adapt and adjust. The agricultural revolution took centuries to fully reshape how humans lived. The Industrial Revolution took a century or more to really transform society from agrarian to industrial. The Information Revolution took decades to go from mainframes to personal computers, to the internet, to smartphones. But each one happened while the previous one was still settling in. There was always some temporal buffer. What we're looking at with quantum AI is something compressed. We're not giving ourselves time to adapt to artificial intelligence before quantum computing potentially transforms it into something else entirely. And unlike past predictions based on speculation and hopes, this one is grounded in mathematics and physics that we actually understand. The danger isn't hypothetical. The danger is that the capabilities could expand so quickly that our ability to control and understand them falls behind. We could build something powerful before we understand what we're building. It's not that super-intelligent quantum AI will suddenly gain consciousness and want to destroy humanity. That's the Hollywood version. The real danger is more subtle. It might become so powerful and so alien that human values and human safety measures might become irrelevant to its operation. Not because it's malicious, but because it's so far beyond human comprehension that our intentions don't matter. But before we get there, we need to understand what quantum computing actually is, because most people's intuition about computers completely fails when you try to understand quantum systems. The failure happens because we're trying to understand something that operates on principles that are fundamentally weird. A classical computer works with logic gates. You take bits as inputs, apply operations, and get bits as outputs. It's deterministic. You can trace through the computation step by step. If you put in the same input, you get the same output. Always. Every time. There's no randomness. It's logical. A quantum computer is fundamentally different in ways that break that logic. A qubit can exist in superposition, which means it's in a combination of multiple states at once. The mathematics describes this as a linear combination of basis states. A qubit could be 0 or 1, or some weighted combination of both. It's not that we don't know which one it is. It literally is both at the same time. But here's the key thing that confuses most people, and why quantum mechanics has this reputation for being incomprehensible. When you measure a qubit, it doesn't remain in superposition. It collapses into either 0 or 1. The superposition vanishes. It's as if the act of measurement forces the quantum system to pick a side. The moment you open the box, the cat is definitely alive or definitely dead. It's no longer both. So while the qubit is in superposition, it's exploring multiple possibilities in parallel. But the moment you observe it, that parallel exploration stops, and you get one answer. This seems paradoxical and contradictory, and it is. That's why even Einstein was disturbed by it. This is where quantum algorithms come in. The trick is to design your computation so that wrong answers interfere with each other and cancel out, while the right answer reinforces itself through a phenomenon called quantum interference. You set up your computation so that the probability amplitudes for incorrect outcomes destroy each other through destructive interference, while the amplitudes for the correct answer add up constructively. It's the same principle as sound waves creating silence through destructive interference. Then when you measure, you're more likely to get the correct result. It's called quantum interference, and it's the secret sauce that makes quantum computers potentially faster than classical computers for certain types of problems. The trick is that this only works if you carefully engineer your algorithm to take advantage of quantum effects. It's not automatic. You can't just throw a problem at a quantum computer and expect it to be faster. You have to fundamentally restructure the problem to exploit the quantum properties. The problems where quantum computers excel are very specific and well understood mathematically. Factoring large numbers is one of the most famous examples. Classical computers would need exponential time to factor a number that's 2,000 bits long. The time required grows exponentially with the number of bits. But a quantum computer running Shor's algorithm could do it in polynomial time. That's an exponential speedup. That's why everyone worries about quantum computers breaking current encryption. All the encryption that protects credit cards and bank accounts and secret government communications uses factorization of large numbers as its mathematical foundation. A large enough quantum computer could crack that in hours. Another area is simulating quantum systems, which sounds obvious, but it's huge. If you want to model how molecules interact, or how electrons behave in a material, or how a new drug might work in a biological system, the number of quantum states explodes so rapidly that classical computers simply cannot handle it. The number of states grows exponentially with the number of electrons. A classical computer can simulate maybe 50 electrons before running out of memory and compute. A quantum computer could simulate a molecule with thousands of electrons because it's also a quantum system. It's using quantum to model quantum directly. Optimization problems are another area where quantum algorithms might help. Finding the best solution among a vast number of possibilities is something quantum computers could theoretically handle better than classical systems through quantum walks and other techniques. Machine learning is also on the list of potential quantum applications. Some researchers believe quantum algorithms could train neural networks faster, or explore solution spaces more efficiently, or find patterns in data that classical systems would miss. But, and this is important, we still don't know exactly how much of an advantage quantum computers will have in the real world. The theoretical advantages are enormous, yes, but practical quantum computers have massive issues. Decoherence causes errors constantly. Every interaction with the environment can destroy your quantum state. Error correction requires adding many physical qubits to create fewer, reliable logical qubits. The overhead is enormous. We might need millions of physical qubits to get the equivalent computing power of thousands of reliable logical qubits. That assumes we can actually build error-corrected quantum computers, which is still an unsolved engineering problem. We're not even sure it's possible with some quantum computing approaches. To understand the potential collision with AI, you need to know where classical artificial intelligence actually came from and how it's evolved over 70 years. The story starts decades ago with the original vision of artificial intelligence. Back in the 1950s, right after World War II, computer scientists imagined building machines that could think like humans. The reasoning was simple and optimistic. If we could understand how human intelligence worked, we could replicate it in code. They were kind of right and kind of wrong in equal measure. The problem was that human intelligence is staggeringly complex and works through mechanisms we still barely understand, even today. The brain has 100 billion neurons, with trillions of connections. The rules governing how it works are not few and barely understood. So instead of building human-like AI, researchers had to build specialized systems that could handle specific tasks in narrow domains. Expert systems ruled the 1970s and 1980s. You'd encode expert knowledge into a system, all the rules and heuristics that a human expert would use, and it could make decisions in narrow domains. A system to diagnose diseases, a system to configure computer hardware, a system to balance chemical equations. It worked pretty well for well-defined problems where the rules were clear and the domain was constrained, but it failed catastrophically as soon as you tried to apply it to anything outside that narrow domain. The knowledge didn't transfer, the rules didn't generalize. Then came machine learning, a fundamentally different approach. Instead of encoding knowledge explicitly by hand, you let the computer learn patterns from data. You show it thousands of examples of dogs and cats, and it learns to recognize the difference. You don't tell it what features to look for. It figures them out on its own. This was revolutionary because you didn't need to manually encode all the rules. The system figured them out from experience. The computer became the expert, learning through examples rather than being told. Deep learning exploded in the last 15 years because of three converging factors that all happened at the same time. First, we finally had access to massive amounts of data, thanks to the internet and sensors everywhere. Billions of images on the internet, trillions of words of text, millions of hours of video. Data was no longer scarce. Second, we had enough computing power to train very large neural networks. GPUs originally designed for video games turned out to be good at the matrix multiplications required by neural networks. Suddenly, you could train networks with millions of parameters where before you were limited to thousands. Third, we figured out better architectures and training techniques, convolutional neural networks for image processing, recurrent neural networks for sequences, transformers for language, batch normalization, dropout, better activation functions, better optimization algorithms. Deep learning showed that if you have enough data and enough compute, you can build systems that perform incredibly well on pattern recognition, classification, and even generation tasks. Image net recognition jumped from 70% accuracy to 98% accuracy in about 5 years when deep learning arrived. Machine translation, which was basically unsolved, became decent. Speech recognition, which required handcrafted features, suddenly worked much better with deep learning. All of these jumped forward dramatically and stayed forward. The current frontier of AI is large language models and multimodal systems that combine vision and language. These systems have hundreds of billions of parameters. Some have trillions. They're trained on trillions of words of text scraped from the internet. They've been fine-tuned using reinforcement learning from human feedback. And they can do things like writing essays that sound like they were written by a human, answering complex questions, writing code that actually works, and reasoning through problems in ways that surprised everyone, including the researchers who built them. Models like GPT-4 and Claude can score in the 88th percentile on the bar exam. They can solve complex math problems. They can engage in abstract reasoning. But here's what's important to understand about all of this progress. All of it is running on classical computers, computers built using silicon transistors that are either on or off, computers that process information using bits that are 0 or 1. Every single operation that ChatGPT or Claude or any other large language model performs is just billions and billions of logical operations happening on classical bits. Add, multiply, compare, branch, repeat billions of times. We've gotten tremendously far using classical computing. We've built systems that can pass standardized tests. We've built systems that can write code. But we're starting to see the limits clearly now. Training larger and larger models requires exponentially more compute. Energy consumption is becoming a serious concern that can't be ignored. Data centers training large models consume massive amounts of electricity. We're talking about the power consumption of a small city just to train one model. That translates to carbon emissions and environmental impact that's becoming harder to justify. The models have started showing diminishing returns. The performance improvements are getting smaller relative to the computing resources required. You can scale up a model by 10 times the compute and get maybe 2% better performance. That's not sustainable. And there are fundamental limitations to what you can do with classical architectures. The way neural networks work is through matrix multiplication and nonlinear transformations. These are deterministic operations. The same input always produces the same output, every time. There's no randomness in the computation itself, though there is in the training process. Innovation in AI on classical computers means finding new architectures, new training techniques, and scaling things up. But there might be computational limits to how far this can go. We might be approaching a ceiling. Not a hard stop where progress stops completely, but a region where progress becomes much harder and much more expensive. This is where quantum computing becomes interesting and potentially dangerous. Imagine a quantum computer-enhanced neural network, a system that can explore solution spaces using quantum superposition. In theory, you could encode information about your neural network into quantum states. You could use quantum algorithms to explore the solution space more efficiently. You could potentially train models faster or achieve better generalization to new data. There are multiple research groups working on this right now. IBM has a quantum machine learning team. Google is exploring quantum neural networks. Microsoft is investigating quantum classical hybrid approaches. Universities around the world are publishing papers on quantum optimization algorithms. Some of the early results are promising, though still limited by the weakness of current quantum hardware. But here's what keeps researchers up at night. We don't fully know what a large quantum neural network could do if we could build one. We don't know if combining quantum computing's exponential state space exploration with artificial intelligence's pattern finding could produce something qualitatively different, something that behaves in unexpected ways. The first whispers of quantum A are just starting to be published in academic journals. Papers are appearing about quantum generative models that could potentially create new data that resembles training data but has properties quantum systems exploit. Quantum reinforcement learning algorithms that could explore game states or optimization landscapes faster than classical algorithms. Quantum versions of common machine learning techniques like support vector machines and nearest neighbor algorithms. Variational quantum algorithms that might be suited to specific machine learning tasks. It's all theoretical and experimental at this stage, but the research is active. The real question is whether quantum A would be faster or better in ways that matter for real applications. And the answer is, honestly, we don't fully know yet. Quantum computing for machine learning is still very much in the theoretical and early experimental phase. Most real-world tests have been on toy problems or simulations designed to show quantum advantage rather than practical applications. We don't have a general-purpose quantum computer powerful enough to train a model that would be competitive with classical approaches on real problems. But that might change if someone figures out how to build error-corrected quantum computers with thousands of logical qubits, and if quantum machine learning algorithms prove to have real advantages over classical methods, then suddenly the entire landscape of AI could shift fundamentally. And here's the terrifying part of it all. We don't have good visibility into what that shift would mean. Classical AI, for all its power and mystery, is still somewhat interpretable in certain ways. We can look at a neural network and understand, to some degree, what patterns it's learned. We can analyze its responses. We can debug it. We can test it. We can probe it. With quantum AI, these certainties evaporate like steam. A quantum system exploring superposition might find solutions to problems that we don't understand. It might find patterns in data that exist in quantum state space that we can't directly observe without collapsing the superposition. When you measure, you get a result, but you've lost the quantum information. You've destroyed the very thing you wanted to understand. It's like asking someone who can see all possible colors simultaneously, plus ultraviolet and infrared, to describe what they see using only words for red, green, and blue. The best answer they can give will be incomplete and potentially misleading, and that person knows they're leaving out information they can't express. And then there's the issue of control and safety. Right now, artificial intelligence researchers worry constantly about alignment. How do you make sure a powerful AI system pursues goals that align with human values and human safety? We've got various approaches being explored. Reinforcement learning from human feedback, where humans rate outputs. Interpretability research trying to understand what neural networks are doing. Adversarial testing to find failure modes. Red teaming, where people try to break the system. And so on. But all of these assume you're dealing with a system you can at least partially understand. You can run tests. You can examine outputs. You can find failure modes. You can identify catastrophic failures. What do you do when the system's internal states are quantum superpositions that collapse when observed? How do you test a system when measuring its state destroys the quantum information? How do you put guardrails on something you can't directly inspect without ruining the very property that makes it work? These aren't purely theoretical concerns. They're real engineering challenges that would need to be solved. And they're being studied, but mostly by researchers who fully understand that we might not find good answers before the technology advances past our ability to control it. The collision of these two revolutions isn't inevitable. That's the thing. It's possible that quantum computers turn out to be much harder to build than anyone expects and remain laboratory curiosities for decades or longer. It's possible that classical AI plateaus before quantum algorithms provide significant advantages. It's possible that quantum machine learning turns out to be a dead end, much like quantum cryptography has been more promise than actual delivery. But it's also possible that we're massively underestimating how quickly these fields will advance. Moore's law has slowed, sure, but it hasn't stopped completely. New materials, new architectures, new approaches might accelerate quantum computing development dramatically. And artificial intelligence is attracting enormous amounts of capital and talent and institutional investment. Money and focus tend to overcome engineering problems that seemed insurmountable just years before. So the question isn't whether quantum AI is possible. The question is, what do we do in the meantime? How do we prepare for a technology that might be transformative or might be nothing at all? How do we make sure that when quantum and AI do collide, if they collide, we're actually ready for what comes next? The answer to what comes next starts with understanding what a quantum computer actually is, because the differences go much deeper than just speed. A classical bit is simple. It's 0 or 1, off or on, true or false, binary. Everything a classical computer does is built on those binary choices cascading through billions of transistors. Think of it like a light switch. It's either up or down, nothing in between. But a qubit, a quantum bit, operates on completely different principles. It can be 0, it can be 1, or it can be both at the same time. This is called superposition. That's the first real difference. Not that qubits are faster processors of the same 0 and 1 logic, but that they exist in a fundamentally different state. They can represent both possibilities simultaneously until you measure them. For centuries, physics worked on the assumption that something had to be in one state or another. You couldn't be here and there at the same time. You couldn't be moving and stationary simultaneously. That's common sense. That's how the world appears to us at human scales. But quantum physics broke that assumption entirely. At the quantum scale, particles really do exist in multiple states at once. They're described by wave functions that represent probabilities rather than definite positions or velocities. An electron orbiting an atom isn't in a specific circular path like we imagine it in textbooks with neat planetary-style orbits. It exists in a cloud of probability around the nucleus. It could be detected anywhere in that cloud when you measure it, depending on the quantum state. This is the fundamental weirdness of quantum mechanics that bothered Einstein so much. The mathematics works perfectly. The predictions are accurate to absurd precision. We've tested quantum mechanics in countless experiments, and it's never been wrong. But the interpretation, what it means about reality, what's actually happening when we're not looking, remains controversial after a century of debate. Physicists still disagree about whether those possibilities are real or just mathematical tools for calculating probabilities. For a qubit to work as a computational tool, you need to be able to put it into superposition, manipulate it using quantum gates, and then use quantum interference to extract useful information. You can't just measure a qubit in superposition and get two answers at once. You get one or the other. The measurement collapses the superposition. One of the possibilities becomes real and the others vanish. The probability of getting each outcome depends on the quantum amplitudes, the mathematical coefficients that describe the strength of each possibility. So how does superposition actually help with computation if you only get one answer? The answer is quantum interference. If you design your computation carefully, you can arrange it so that wrong answers interfere destructively with each other and cancel out through negative interference, while the right answer interferes constructively and amplifies through positive interference. It's like noise-cancelling headphones where out-of-phase sound waves cancel each other out, but waves that are in phase add together and get louder and louder. You set up your quantum computation to be a similar pattern of interference, where the answer you want gets louder through constructive interference, and the wrong answers get quieter through destructive interference until they're nearly zero probability. You apply quantum gates, basic quantum operations, to manipulate the qubits in precise ways. Single qubit gates that rotate the quantum state around axes in Hilbert space. 2 qubit gates that create entanglement between qubits and link their states together. You engineer the sequence of gates so that interference patterns create amplification for correct answers and suppression for wrong answers. Then, when you measure at the end, you're more likely to get the right result because its probability amplitude is higher after all the interference. The probability distribution is shaped by the quantum circuit. This is the real power of quantum computing. Not that it magically knows all answers at once, but that it can explore vast numbers of possibilities in parallel through superposition, and then use interference effects to amplify the correct answer and suppress the wrong ones. It's elegant in theory. A quantum computer with just 30 qubits can represent over 1 billion states in superposition simultaneously. Each additional qubit doubles the number of simultaneous states. It's exponential. With 50 qubits, a quadrillion different states at the same time. With 300 qubits, you're dealing with more simultaneous states than there are atoms in the observable universe, 2 to the 300th power. That number is so incomprehensibly large that it becomes almost meaningless to human intuition. We don't have analogies big enough to make sense of it. But here's the critical catch that ruins everything. That exponential scaling only works if the qubits stay in superposition and if you can maintain quantum coherence long enough to perform your entire computation. If decoherence destroys your quantum state halfway through, you lose everything. All that potential computation vanishes. The superposition collapses randomly and you get a wrong answer. In reality, this is brutally difficult. It's the main obstacle preventing quantum computers from being practical right now. The biggest enemy of a quantum computer is decoherence. Decoherence is what happens when a quantum system interacts with its environment. A stray photon of light hits the qubit. A vibration from nearby equipment disturbs it. Heat causes atoms to jiggle and destroy the quantum state. Thermal energy at room temperature is enough to destroy quantum coherence almost instantly. Cosmic radiation passes through. Electromagnetic radiation from any source interferes. The qubit loses its superposition and collapses into a definite state. It's like trying to balance a pencil on its point. Theoretically possible, sure, but the slightest breeze will knock it over. Qubits are even more fragile than that metaphor suggests. They need to be isolated from electromagnetic radiation as much as humanly possible. The RF shielding needs to be comprehensive. They need to be kept at temperatures near absolute zero. We're talking fractions of a degree above 0 Kelvin. Some systems use dilution refrigerators that can cool to millikelvin temperatures. That's 1,000th of a degree above absolute zero. They need to be insulated from vibrations to nearly impossible levels of precision. You need seismic isolation to keep ground vibrations from destroying your quantum state. You need vibration isolation platforms. You need active vibration cancellation. You need RF shielding to keep stray radio signals out. You need magnetic field shielding to keep Earth's magnetic field from interfering with the quantum states. The engineering challenge is just immense. It's like trying to build a laboratory inside a laboratory inside a laboratory. The best quantum computers today operate with qubits that stay coherent for microseconds to milliseconds, depending on the approach. A microsecond is 1/1,000,000th of a second. A millisecond is 1,000th of a second. During that tiny window of time, the quantum computer has to perform all its calculations, find its answer, and measure the result before the quantum state collapses, and you lose everything. It's like trying to write a complete novel while the page is slowly erasing itself. If you're too slow, you lose your work. Most quantum computer companies are using different physical approaches to create qubits because we still don't know which one will win. It's like the early days of computing when there were dozens of different technologies competing to build computers. Some use trapped ions, actual atoms held in place by electromagnetic fields in a vacuum chamber. Ionization traps use laser beams to manipulate ions and measure their states. IonQ is going down this path. Some use superconducting circuits, tiny loops of metal that become superconducting at near absolute zero temperatures. When you cool them below a certain temperature, they have zero electrical resistance and can maintain quantum states. Google and IBM have both invested heavily in superconducting qubits. Some use photons, actual particles of light manipulated using optics. Xanadu is working on photonic quantum computing. Some use neutral atoms held in optical traps using laser beams as tweezers. Quera and other companies are pursuing neutral atom approaches. Each approach has different advantages and disadvantages that affect their viability. Trapped ions have very long coherence times, potentially hours or more in principle, which is amazing. You could run very long calculations without decoherence destroying everything, but they're incredibly hard to scale up to thousands or millions of qubits. Building a quantum computer with 1,000 trapped ions is an engineering nightmare. Each ion needs to be isolated and controlled individually. Superconducting qubits can be scaled better because they're easier to manufacture using existing semiconductor fabrication techniques. You can put thousands of them on a single chip, but they have shorter coherence times, usually microseconds, and higher error rates. The quantum information is very fragile. Photonic qubits don't need extreme cooling, which is nice and reduces engineering challenges. But photons are hard to manipulate and store and detect reliably. Neutral atoms held in optical tweezers are promising and have reasonable coherence times, but are still mostly experimental. No one has built a large commercial system yet. None of these approaches are clearly the winner yet. This is still the early days where people are trying different architectures, and whoever figures out the right approach The one that can be scaled reliably to thousands or millions of qubits with low error rates and reasonable coherence times will probably win the race and dominate quantum computing for decades. The barrier to entry is low enough that new approaches can still succeed. Another critical problem beyond just decoherence is entanglement. Entanglement is related to superposition, but it's actually different in important ways. Entanglement is when two or more qubits become linked in a way that measuring one instantly affects the other, regardless of distance or time. Einstein called this spooky action at a distance, and he hated it viscerally. He thought it meant quantum mechanics was incomplete, that there had to be hidden variables we weren't seeing that would restore locality and determinism to physics. But experiment after experiment, test after test, has shown that Einstein was wrong about this. Entanglement is real and verified, and it's one of the most powerful features of quantum computing. Entanglement lets you correlate the states of multiple qubits so that they work together in coordinated ways that are impossible classically. If you want to run a quantum algorithm on 50 qubits, you don't just need 50 independent qubits all in superposition. You need those qubits to be entangled in specific patterns designed by your algorithm. The algorithm has to create specific entanglement structures. Creating and maintaining that entanglement requires precise control over each qubit and the interactions between them. You have to choreograph all those qubits to be in the exact right entangled state, all at the same time, without any of them decohering. It's technically challenging because entanglement is even more fragile than superposition alone. The slightest noise or error can break the entangled state. One stray photon can destroy the entire correlated state you spent microseconds building. And you can't just measure to check if the entanglement is still there, because measurement destroys it. So you're flying blind, hoping the system is still entangled properly, not knowing until you measure at the very end. This is where error correction comes in. And this is where quantum computing becomes almost impossibly complicated. In a classical computer, if a bit is corrupted, you can protect it using error-correcting codes. You store redundant copies of the information. If one copy gets flipped, you can compare with the other copies and figure out which bit is wrong and fix it. You can detect and correct errors. It's tedious, but conceptually straightforward. But quantum systems have a fundamental problem called the no-cloning theorem. You can't copy a quantum state. It's not just that we haven't figured out how to do it yet. It's mathematically impossible due to the rules of quantum mechanics. You can't measure a quantum state without destroying it. So you can't protect quantum information the way you protect classical information using redundant copies. Instead, quantum error correction uses a completely different strategy. You spread the quantum information across multiple physical qubits in an entangled state so that you can detect errors without directly measuring the quantum state and destroying it. If a bit gets flipped due to noise, the error-correcting code can identify which qubit was affected and fix it by applying the right quantum operations. But this requires massive overhead. You need many extra physical qubits just to store the error correction information. Current estimates suggest you need around 1,000 physical qubits to create one reliable logical qubit that actually preserves quantum information reliably. That means to build a useful quantum computer with 1,000 logical qubits, sufficient to run meaningful algorithms. You'd need about 1 million physical qubits, maybe more. We're nowhere near that. The best current quantum computers have maybe a few hundred qubits, and those qubits have error rates that are still too high for long calculations. The reality is that we're still in the early stages of quantum computing development, perhaps equivalent to where classical computers were in the 1950s, before the transistor had been perfected, and before anyone really knew if they'd ever be useful for practical problems. So what's the actual advantage of quantum computing for the specific problems it's designed to solve? There are only a few areas where quantum algorithms have been proven mathematically to have exponential speed up over the best classical algorithms. Finding quantum algorithms with exponential speedup is actually really hard. Most problems don't have one. Most quantum researchers have been working on quantum machine learning for decades and haven't found exponential speedups for most ML problems. The most famous quantum algorithm is Shor's algorithm for factoring large numbers. This is the one that makes people nervous about encryption. On a classical computer using the best-known algorithms, factoring a 2000-bit number would take roughly 2 to the 2000th operations. That's a number so large that it would take longer than the age of the universe to complete the calculation, even if you had a computer that could perform 1 trillion operations per second. The time grows exponentially with the size of the number. But on a quantum computer running Shor's algorithm, the same 2000-bit number could be factored in a few hours. A few hours versus the age of the universe. That's an exponential speed up. That's roughly 1 billion times faster, give or take a few orders of magnitude. That's why everyone worries about quantum computers breaking encryption. The encryption that protects credit cards, bank accounts, secret government communications, state secrets, everything, all of it relies on the mathematical assumption that factoring is hard. If someone builds a large enough quantum computer with low enough error rates, that assumption becomes false. Every encrypted message you've ever sent could potentially be cracked retroactively if someone stores the encrypted data and waits for a quantum computer. People are already talking about quantum-safe encryption, new encryption schemes that would still be secure even against a quantum computer running Shor's algorithm. Another area where quantum computers have proven advantage is simulating quantum systems. If you want to model how molecules behave or how electrons interact in a new material, or how a drug might bind to a protein, or how a catalyst might work, the problem size grows exponentially with the number of particles on a classical computer. The state space of a quantum system with 100 electrons is so enormous that even the most powerful classical supercomputers in the world couldn't simulate it exactly. We're talking about supercomputers with millions of cores and petabytes of memory still not being enough. A molecule with 100 electrons has a state space with more possibilities than 10 to the 30th power. That's a 1 followed by 30 zeros. A classical computer trying to track all those possibilities would need more memory than exists in the universe. A quantum computer, being a quantum system itself, can simulate quantum systems directly through its own quantum operations. It's like using a guitar to understand how another guitar works, or using a laser to study the behavior of other lasers. You're using the same physics to model the same physics. The quantum computer's quantum states directly represent the quantum states you're trying to understand. That makes it inherently faster. This is one of the applications that physicists and chemists are most excited about because it could revolutionize drug discovery and materials science. Instead of running expensive physical experiments that take months, or doing brute force classical simulations that take weeks, you could potentially use a quantum computer to model how molecules interact in hours or minutes. You could discover new drugs faster. You could design new materials with specific properties without building and testing thousands of prototypes. You could accelerate the entire drug development pipeline from decade-long processes to year-long processes. This application alone might justify building large quantum computers. There are also quantum algorithms for optimization problems, finding the best solution among a vast number of possibilities when you're searching a huge landscape of potential options. Imagine trying to find the shortest route visiting 100 cities. The number of possible routes is astronomically large. A quantum computer could search through many of those routes in parallel through superposition and use interference to amplify good solutions. And quantum machine learning algorithms that might be accelerated by quantum computers. Algorithms for classification, regression, dimensionality reduction. But, and this is important, for many real-world problems, the quantum advantage is not as dramatic as the textbook examples suggest. Many problems don't have a known quantum algorithm that provides exponential speedup. For those problems, quantum computers might be faster, maybe significantly faster, maybe 10 times faster, or 100 times faster, but not by an exponential factor, polynomial speedup instead of exponential speedup. That's still useful in practice, but much less dramatic than the theoretical papers suggest. And the quantum advantage often only appears for very large problem sizes. Problem sizes that might be impractical or might not even be relevant to real-world applications. You might get a speedup for problems with 1 million variables, but face problems with 1,000 variable inputs. The advantage in theory doesn't always translate to advantage in practice. There's also the question of practical hybrid systems. In reality, quantum computers won't replace classical computers. Instead, there'll be hybrid systems where quantum processors handle specific subtasks that they're good at, while classical computers handle the rest. You might use a quantum processor for the optimization phase of a machine learning algorithm, while using classical systems for data pre-processing and result interpretation. Or you might use quantum simulation for molecular modeling, while using classical systems for the rest of the drug discovery pipeline. These hybrid approaches might be the most practical path forward, where quantum and classical computing work together rather than one replacing the other. Most researchers in the field think this is the realistic future, not quantum computers ruling alone, but quantum classical systems working in tandem on problems too complex for classical alone. The real state of quantum computing today is this. We have working quantum computers with dozens to a few hundred qubits that actually exist and function in laboratories around the world. They can perform calculations that would be impossible to verify on classical computers for specific, carefully designed problems. But those achievements are more like proofs of concept than practical applications. They're more like we showed the technology works in principle demonstrations than this solves a real-world problem better than classical computers' demonstrations. The quantum computers are still so limited by decoherence and error rates and coherence time that they can't solve real-world problems better than classical computers. They can't train machine learning models faster. They can't factor numbers faster. They can't optimize routes faster. They can't do anything faster that matters. Nothing that anyone actually cares about computing. You could point to Google's quantum supremacy demonstration in 2019, where they claimed their quantum processor solved a specific problem faster than a classical computer. The problem involved simulating quantum circuits, specifically a random quantum circuit of moderate depth. In theory, quantum computers should be good at simulating quantum systems. But the problem was so specialized and artificial, so removed from any practical application, that it didn't demonstrate any real advantage. It was mathematically interesting as a proof that quantum speedup is possible in principle, but practically useless. No one cares about solving that specific random circuit problem faster. No application relies on it. Since then, classical computers have caught up on that specific problem anyway through clever algorithm improvements. The gap has narrowed or disappeared depending on how you count it. The quantum computing companies, IBM, Google, IonQ, Rigetti, and others, are all racing to build better hardware and improve error rates and extend coherence times. But the engineering challenges are immense. Not just engineering, though. We're running into physics limits. Every year, the timelines for commercially useful quantum computers keep getting pushed back. 5 years ago, 10 years ago, people thought we'd have useful quantum computers in 5 to 10 years. We were always 5 to 10 years away. Today, most experts think we need another 10 to 15 years, maybe more. Some pessimistic researchers think it might take 30 years if it's even possible at all with current approaches. Some physicists think we might need completely new physical principles we haven't discovered yet. The hardware is progressing, that's undeniable. We've gotten from a couple of qubits to hundreds, from microsecond coherence times to millisecond coherence times in some systems. But progress is slower than the hype would suggest. We're still dealing with fundamental physics problems, not just engineering challenges. It's physics holding us back. The coherence times aren't improving as fast as we need them to. The error rates aren't improving fast enough. We need both to improve dramatically to get to practical quantum computing. We need error rates to drop by orders of magnitude. We need coherence times to extend by orders of magnitude. The gap between theory and practice remains very large. We're in a valley where the technology is real enough that it feels possible, but far enough away that it remains genuinely uncertain whether we'll actually achieve practical quantum computing in our lifetime. When you talk about what quantum computers could do for artificial intelligence, you need to understand that we're talking about largely theoretical potential at this point, not proven capability. There are papers published about quantum machine learning algorithms. Dozens of papers. Hundreds of papers if you count all the conference proceedings and preprints. There are proposed quantum approaches to training neural networks faster, or exploring solution spaces more efficiently, or finding patterns in high-dimensional data. There are variational quantum algorithms designed specifically for optimization problems, where you're searching through a landscape of possibilities. There are quantum approaches to support vector machines, which are a classical machine learning technique that might be accelerated by quantum speed-up. There are quantum kernel methods for classification. There are quantum approaches to clustering and unsupervised learning, but most of these are still in the simulation stage or the toy problem stage. Researchers test them on tiny problems with maybe 10 to 20 qubits on small toy data, or they simulate them on classical computers rather than running them on actual quantum hardware. No one has built a quantum machine learning system that demonstrates practical advantage over classical systems on a real problem that matters. No one has shown a quantum ML system outperforming classical deep learning on MNIST or CIFAR or ImageNET or any real dataset. That hasn't stopped the excitement and investment though. Multiple research teams at major institutions are investigating quantum neural networks, quantum reinforcement learning, hybrid quantum classical approaches, quantum approaches to optimization problems in machine learning. Google has a quantum AI lab and is actively pursuing quantum machine learning. IBM has a whole quantum machine learning team and regular publications. Microsoft is exploring quantum neural networks through their Azure Quantum Initiative. Amazon has quantum computing services. Universities around the world are publishing papers on quantum approaches to AI. The basic idea is that if you have a quantum computer with thousands of logical qubits and very low error rates, you could encode machine learning problems into quantum states and solve them using quantum algorithms. You could potentially train a neural network by encoding the weights and activations into quantum superpositions and using quantum interference to optimize the weights toward lower loss. The quantum states would explore many possible weight configurations simultaneously through superposition. Through interference, you'd amplify good solutions and suppress bad ones. In theory, this could give you exponential speed up for certain machine learning tasks. You could explore solution spaces exponentially faster. You could find optimal or near-optimal solutions to certain optimization problems that classical computers would take an exponential amount of time to solve. In practice, we don't know if this will work yet. We don't know which machine learning problems would actually benefit from quantum speedup and which ones wouldn't. We don't know if the overhead of encoding the problem into quantum states and then extracting the answer will offset the theoretical quantum advantage. You have to spend time getting training data into quantum states. You have to spend time extracting results back out and interpreting them. That encoding and extraction overhead might completely eliminate any speed benefit you got from quantum acceleration. It's similar to the overhead in matrix multiplication. We don't know if the quantum algorithms will actually outperform classical algorithms in the real world on problems that matter. What we do know is that if quantum computers do provide significant advantages for machine learning, it could be genuinely transformative for artificial intelligence development. A sufficiently powerful quantum machine learning system could potentially train large models much faster than is possible classically, explore solution spaces more comprehensively, find patterns in data that classical systems would miss or never discover in any reasonable time frame. It could accelerate the development and deployment of artificial intelligence in ways we can't fully predict or control. It could let you train on larger datasets It could discover more complex patterns. It could optimize in ways we currently can't with classical systems. It could make feasible what is currently impossible. And that's where the real concern lies for researchers thinking about the future. Not that quantum AI will definitely be dangerous or super intelligent or turn against humanity. That's Hollywood scenario thinking. But that we don't know what it will do. We don't know how powerful it could become. We don't know what capabilities it might unlock. We don't have good visibility into how it would behave or what patterns it might find, or what optimization it might achieve. That uncertainty is the dangerous part. We're potentially building systems we don't fully understand, using hardware we don't fully understand. And here's what really matters about the timing. We're in this weird situation where both revolutions are accelerating simultaneously. Classical AI is improving rapidly, exponentially rapid in some dimensions. New models are released every few months. Quantum computing is improving slowly but steadily. Some progress every year, but not the dramatic breakthroughs the hype promised. Most timelines suggest we're 5 to 10 years away from AI systems that are significantly more capable than what exists today. Maybe capable of handling more complex tasks, reasoning across longer contexts, potentially being more autonomous. Most timelines suggest we're another 10 to 15 years from quantum computers that are useful for practical applications. Useful meaning actually solving problems better than classical computers in ways people care about. Those timelines might not overlap. Classical AI might advance so far that we've already built powerful systems before quantum computers are ready. We might have AGI before we have practical quantum computers, but they might also overlap. What if quantum machine learning becomes viable in 10 years, just as AI systems are becoming more capable than humans at most intellectual tasks? What if the collision happens before we've figured out how to make AI safe and aligned with human values? What if the combination arrives faster than our ability to understand and control it? That's the concern driving research into quantum AI safety, even though quantum computers don't exist yet. Not inevitable disaster, but the possibility of rapid change outpacing our ability to manage it responsibly. But the uncertainty isn't abstract. There are concrete, near-term threats that quantum computers will create regardless of whether AI becomes super-intelligent or not. Real threats. Threats that governments are already preparing for. Threats that could reshape geopolitics and economics. The most immediate one is encryption. Right now, essentially all of our digital communication is protected by mathematical assumptions that became the foundation of modern security decades ago. When you buy something online, your credit card number travels through the internet encrypted. When you send an email, it can be encrypted. When governments communicate, they use encryption. When banks transfer trillions of dollars electronically every day, it's all encrypted. The system works because certain mathematical problems are hard. Factoring large numbers into their prime components is hard on classical computers. So hard that it would take thousands of years to crack a 2,000-bit key using the best algorithms we have. The encryption standard RSA relies on this. Diffie-Hellman key exchange relies on the discrete logarithm problem, which is also hard classically. Elliptic curve cryptography is similar. All of it depends on the assumption that these problems are hard. That assumption is not universal law. It's just that nobody has found a fast way to solve them on classical computers. But quantum computers can solve them fast. Shor's algorithm, which we discussed, can factor large numbers efficiently on a quantum computer. It can solve the discrete logarithm problem. Once a quantum computer powerful enough exists, those encryption schemes become worthless. Not gradually weaker, but instantly obsolete. A key that would take 1,000 years to crack on a classical computer could be cracked in hours on a quantum computer running Shor's algorithm. Now here's where the panic starts setting in. We don't know exactly when this will happen. quantum computer companies keep pushing their timelines. A decade ago, they said we'd have useful quantum computers in 5 years. 5 years later, they said 5 more years. This has been going on for years. Some researchers think it's still 10 to 15 years away. Some think it might be 20 or 30. Some think it might not happen at all with current approaches. But the uncertainty creates a terrifying problem. Any encrypted data that matters, if someone captures it now and stores it, they can crack it later once quantum computers exist. Your secret communications from 20 years ago might be readable in 10 years if you send them today. Your financial records, your medical history, state secrets. Everything encrypted now using these methods could potentially be decrypted retroactively once a sufficiently powerful quantum computer is built. This is called the harvest now, decrypt later attack. Adversaries are probably already doing this. They're collecting encrypted communications, encrypted data, everything important, storing it, waiting for quantum computers to become powerful enough to crack it. Then all of that secretly gathered data becomes readable. That's why governments and organizations around the world are suddenly very interested in quantum-resistant encryption, new encryption schemes that would remain secure even against a quantum computer running Shor's algorithm, post-quantum cryptography. They're trying to transition the entire digital infrastructure of the world to new encryption before quantum computers become powerful enough to break the old ones. But that transition is slow. Governments are working on standards. NIST, the National Institute of Standards and Technology in the US, has been evaluating post-quantum cryptographic algorithms for years. They selected several as standards, algorithms based on lattice problems, hash-based signatures, and other hard mathematical problems that don't have known quantum speedup. But the actual deployment to replace RSA everywhere, in every system, in every device, that's going to take a decade or more. The infrastructure is incomprehensibly large. Billions of devices, billions of connections, legacy systems that can't be updated, old embedded systems that are still critical to infrastructure but won't get patches, power plants, water treatment facilities, electrical grids, all still using old encryption. The transition is not just slow, it's incomplete. Some things will get upgraded, other things will stay vulnerable forever. Legacy systems still using old encryption will be around for decades. Embedded systems that can't be easily updated. Old devices that no longer get security patches. Organizations that don't prioritize the transition. You still see systems running Windows XP or older technology that should have been retired years ago. Now imagine trying to get the entire world to upgrade its encryption in the next 10 years. It's not going to happen. By the time quantum computers are powerful enough to break encryption, a significant portion of the digital world will still be vulnerable. And here's the killer part. Once quantum computers are powerful enough to break RSA, they're also powerful enough to break basically everything else that uses similar assumptions. The whole internet encryption infrastructure becomes compromised at once. Not gradually, not one algorithm at a time. All at once. That's different from classical cryptanalysis, where you might find a clever way to break one algorithm, but others remain secure. With quantum computers, it's like the entire foundation gives way simultaneously. This isn't theoretical. Governments are literally preparing for this. The National Security Agency published guidance about quantum computing and cybersecurity. China is investing heavily in quantum research, probably thinking about both defensive and offensive implications. Russia is doing the same. Everyone with geopolitical interests is positioning themselves. The US government is mandating federal agencies transition to post-quantum cryptography by 2030. That's less than 6 years away. And they're still evaluating standards, still testing implementations. It's chaotic. The transition timelines are already slipping. Organizations can't move that fast. And that's just the encryption apocalypse. The direct, immediate threat from quantum computers breaking existing encryption. That doesn't even touch what quantum AI could do if it arrived at the same time as quantum computers become powerful enough to be genuinely useful for real-world problems. In parallel, quantum computers could revolutionize drug discovery. This is where the promise part of the technology actually delivers real value rather than just breaking things, where the potential benefits are enormous, where the impact could be genuinely positive if deployed wisely. Molecules are quantum systems. They have quantum properties. Electrons around atoms, molecular bonds, how molecules interact with each other, all quantum phenomena. When you're designing a new drug, you need to know how it will bind to proteins, what shape it takes in different environments, how your body will metabolize it. Traditionally, you do this through expensive physical experiments and through classical computer simulations. You synthesize the drug in a lab, test it, see if it works, or you run simulations on a classical computer predicting molecular behavior. But the simulation costs scale exponentially with the complexity of the molecule. A drug molecule might have dozens of atoms, hundreds of electrons. The quantum state space is enormous. Classical computers can't efficiently model it for large molecules. They have to make approximations and shortcuts that lose information. A quantum computer, being a quantum system itself, can directly simulate quantum systems. You encode the molecule into quantum states and let quantum mechanics do the calculation naturally. You don't have to approximate anything. You get the actual answer. This could speed up drug discovery dramatically. Instead of spending years and billions of dollars testing candidate drugs, you could simulate thousands of candidates virtually, narrow it down to the most promising ones, then test only those in the lab. You could find new drugs faster. You could discover new medications for diseases nobody has good treatments for. You could design antibiotics that bacteria can't develop resistance to. You could optimize cancer treatments. You could revolutionize medicine. This is probably the clearest case of quantum computing providing genuine, unambiguous benefit to humanity. Consider the current state of drug development. It takes on average 15 years and billions of dollars to bring a new drug to market. You need to synthesize thousands of candidates, test them, eliminate the ones that don't work, refine the promising ones, deal with side effects, handle FDA approval processes, clinical trials, everything. Most drug candidates fail. You might test 10,000 compounds and only one makes it to market. That's the scale of the problem. A quantum computer could change that. Instead of testing thousands of physical compounds, you simulate hundreds of thousands of virtual compounds. You can model how they bind to their target proteins. You can predict side effects by simulating how they interact with off-target proteins. You can predict metabolism by simulating enzymatic reactions. You can predict toxicity by simulating cellular responses, all in silico, all on a computer. Then you only synthesize and test the ones the quantum simulation said would work. You've compressed years of testing into weeks of simulation. That's transformative. It means diseases we can't currently treat become treatable. Cancer drugs that are more effective. Treatments for neurodegenerative diseases. Antibiotics that overcome resistance. The promise is enormous. And it's also where quantum AI enters the picture most naturally. Because what if you combine quantum computers' ability to simulate molecular behavior with AI's ability to recognize patterns across millions of simulations? What if you have an AI system that's running on a quantum computer that's simulating molecular space and searching through it, looking for drug candidates that have specific properties? The AI could learn what makes a good drug molecule. It could learn the patterns in molecular structure that correlate with efficacy, with low toxicity, with good bioavailability. It could then generate new candidate molecules that match those patterns. It could search through theoretical drug space, a space so large that a classical computer couldn't explore it in any reasonable time. And because the search is happening on a quantum computer using quantum superposition, it's exploring billions of possibilities in parallel. The AI finds patterns in what's possible before you ever build anything in the lab. It discovers molecular structures that humans never would have considered. It finds overlooked possibilities. It identifies relationships in chemical space that classical analysis missed. This could compress decades of research into years, or years into months. The promise is real. A quantum AI system optimized for drug discovery could change medicine forever. It could find cures we've been searching for. It could save millions of lives. It could do genuine good in the world. But there's a catch. That same capability, quantum computers searching through vast spaces efficiently while AI finds patterns, works for anything you want to optimize, anything at all. So imagine quantum AI applied to financial systems. Financial markets operate on massive optimization problems. You're trying to predict prices, find arbitrage opportunities, identify assets that are mispriced relative to their intrinsic value. Classical computers run trading algorithms constantly, but they're limited by the search space they can explore. A quantum AI system could search through far more trading strategies simultaneously. It could find patterns in market data that classical systems would take decades to discover. It could identify exploitable inefficiencies in markets and extract value. Now that sounds nice if you're a financial institution that can build a quantum AI trading system. You become absurdly profitable. But what happens to everyone else? To financial markets as a whole? If one organization has a quantum AI advantage in trading and others don't, that organization captures value at the expense of everyone else. They're not creating value, just extracting it differently. The market becomes a place where a quantum-enabled financial firm predates on everyone else. And if multiple organizations have quantum AI systems all competing for the same arbitrage opportunities, they can destabilize markets. They can create feedback loops where quantum AI trading algorithms interact with each other in ways that create crashes or bubbles. Systems of quantum AI traders all competing, all discovering the same exploitable strategies at the same time, all trying to execute at once, that could cascade into systemic crises. Humans already struggle to understand modern high-frequency trading. Adding quantum AI to that situation could make it exponentially worse. We've had flash crashes triggered by algorithmic trading. Market circuit breakers exist because algorithms can trigger sell-offs that cascade faster than humans can respond. Now imagine quantum AI trading systems that are discovering and executing strategies in microseconds that classical trading algorithms would take milliseconds to execute. The speed advantage creates instability. The exploration of search space creates discovery of new exploit strategies. The combination creates a system we might not be able to control or even understand. Similarly, for optimization of supply chains, resource allocation, production planning, logistics, every industry has optimization problems. Quantum AI solving them means whoever has it first gets massive competitive advantages. It means the concentration of wealth and power accelerates. It means gaps between organizations that have quantum AI and those that don't become unbridgeable. Whoever controls quantum AI in a particular industry comes to dominate that industry. And then there's the possibility that quantum AI optimization finds solutions that are technically correct but ethically horrifying. The optimization might find the most efficient way to run a factory, but that efficiency comes from practices that harm workers. Maybe workers injured at higher rates, but it saves on safety equipment costs. Maybe unsafe conditions, but it saves on compliance costs. It might find the most profitable way to manage a power grid, but that comes at the cost of reliability for poor neighborhoods. Cut service to unprofitable areas. Profitable. It might find the most cost-effective way to run a healthcare system, but that means denying treatment to unprofitable patients. Sick people who can't afford expensive treatments get denied care. The optimization looks at the problem and finds the mathematically perfect solution. Humans look at that solution and recoil in horror. It does everything you asked, but not what you wanted. The AI optimizes for what you tell it to optimize for. If you tell it to maximize profit, it maximizes profit. It doesn't care about the human cost. It doesn't care about fairness or dignity or anything except the metric you've defined. This is the famous alignment problem, not just for quantum AI, but for all AI. The problem of specifying what you actually want versus what you think you want. And because the search space is so large, the optimization so powerful, the solution it finds might involve strategies that humans would never have thought to try. It might discover that certain groups should be excluded from a service because that optimizes the metric. It might discover that lying in specific ways increases the metric, saying something is cheaper than it is to attract customers, misrepresenting product quality to increase sales. It might discover solutions that are legal but deeply immoral, loopholes nobody else found, strategies that exploit edge cases in regulations. It might discover that paying off regulators is cheaper than compliance, or that funding politicians to weaken regulations is more profitable than following them. The system is searching through optimization space and finding the path of least resistance. Quantum AI optimization amplifies these problems because the search is more exhaustive and the solutions are less interpretable. A classical AI optimizing over millions of possibilities is hard to understand. A quantum AI optimizing over trillions of possibilities becomes black box. The answer it finds is correct mathematically, but opaque practically. Why did it choose that? What pattern did it find? You might not be able to tell. The quantum interference patterns that led to that solution aren't easily traced or explained. You just see the answer. You have to trust that it's right. And sometimes it is right mathematically while being deeply wrong practically. And this brings us back to the core problem of AI alignment, but in a quantum context. We're already struggling to align classical AI systems. We're still trying to figure out how to make neural networks do what we actually want, rather than gaming the metric we've defined. We're designing reward functions that don't have unintended consequences. We're building interpretability tools to understand what the AI learned. We're testing for robustness and safety in edge cases. It's a huge amount of work, and we're still failing at it regularly. The problem is that every time you specify what you want the AI to optimize for, there are edge cases you didn't think of, unintended ways the AI can satisfy the specification that you didn't anticipate. A famous example is reinforcement learning systems that learn to cheat their training environment to maximize the reward signal. They learn the rules of the game faster than you expected, and they exploit those rules in ways that weren't the intended solution. An AI trained to avoid obstacles learns to crash into the boundary of the simulation instead of truly navigating. An AI trained to maximize coins in a video game learns a glitch that generates infinite coins. These are small examples, but they illustrate the core issue. The AI is doing exactly what you told it to do. It's just that what you told it to do and what you actually wanted were different things. Now imagine that same alignment problem, but with a system that's running on a quantum computer, an AI system that can explore search spaces exponentially larger. An AI system whose solutions are even less interpretable because they're found through quantum interference patterns. An AI system that might find strategies that classical AI would miss entirely. Strategies so clever, so unexpected, so far outside the box of human thinking that we wouldn't recognize them as exploits. The alignment becomes harder. You can't just run tests on it because the quantum coherence might break. You can't just measure intermediate states to check if it's on track because measurement collapses the quantum state. You can't know what the AI is computing during the process. You only know the answer at the end when you measure. You can't just scale up your existing alignment techniques because those were designed for classical systems, where you can inspect intermediate states, where you can understand the computation, where you can trace back how the system arrived at an answer. In a quantum system, much of that visibility is lost. The computation happens in superposition. You can't measure during computation without breaking the superposition. You can only measure at the end. You have to invent new alignment techniques for quantum AI, new frameworks for verification and safety, new ways to understand what a quantum AI system is doing. And we haven't done that. We don't even have frameworks for it yet. We don't know what alignment looks like for a system computing through quantum interference. The technical challenges are immense. We're already running behind on AI alignment for classical systems. We're probably going to run behind on quantum AI alignment too. The timing is going to be brutal. We need to develop quantum computers, which is already hard. We need to develop quantum AI algorithms that are useful, which requires both quantum computing expertise and ML expertise. We need to align both the quantum computers and the AI systems running on them, which requires expertise in quantum physics, AI safety, interpretability, verification, testing, everything. We need to do all of this with political pressure to move fast and deployment incentives pushing toward moving faster. In that environment, safety gets neglected. Safety always gets neglected when there's pressure to move fast. We're seeing it already with classical AI, companies pushing models to production before they're adequately tested, regulators struggling to keep up, safety researchers outnumbered by development teams, competitive pressure driving the incentive to move fast over the incentive to be careful. Quantum AI will be the same, except worse, because the technical barriers are higher, so there are fewer independent labs and teams working on it, fewer perspectives, fewer competing approaches, more concentration in the hands of well-funded organizations with less oversight. The people working on quantum AI will be physicists and quantum computing engineers and ML researchers. Very few of them will be AI safety researchers. There won't be enough safety expertise in the room to push back on technical pressure to deploy faster. The safety people will be minority voices saying, slow down, test more carefully, we need to verify alignment, and the pressure will be immense. Geopolitical pressure from countries trying to be first, corporate pressure from organizations trying to gain advantage. The incentive structure will all point toward moving fast and taking risks. When Google announced quantum supremacy in 2019, they did something interesting. They built a quantum computer with 53 qubits, and they used it to perform a specific computation that was designed to be hard for a classical computer to verify, but easy for a quantum computer if the system works correctly. The computation involved simulating a random quantum circuit of moderate depth. They ran the quantum computer and got an answer in 200 seconds. They estimated that the best classical supercomputer in the world would need about 10,000 years to solve the same problem. Quantum supremacy. They'd proven that quantum computers could do something faster than classical computers. It was a milestone. It was also misleading. The problem was completely artificial. No one cares about simulating random quantum circuits. There's no application. There's no utility. It's not solving any real problem. It's solving a problem designed specifically to show quantum advantage. It's like proving you can run 100 miles per hour by driving on an empty track in the middle of the night with perfect conditions. Sure, you're faster than a car driving on a regular highway with traffic. But that doesn't prove the fast car is useful. It just proves it exists. And there's another issue with the supremacy claim. The classical computer estimate of 10,000 years was based on a specific algorithm, a specific implementation, assumptions about how the problem would be tackled, but researchers have been clever. They've optimized classical algorithms for similar problems. They've used tensor network methods and other mathematical tricks. They've implemented these algorithms on GPU clusters. They've gotten the runtime way down. Classical computers have caught up on that specific problem since 2019. Researchers at IBM and others developed better classical algorithms. They optimized implementations. They've narrowed the gap or closed it entirely, depending on how you measure. Google still claims they're ahead, but the advantage is way smaller than originally claimed. We're talking maybe an order of magnitude faster instead of 10,000 times faster. And IBM has argued, credibly, that with better classical algorithms, the gap would close entirely. The point of quantum supremacy was supposed to demonstrate that there's a regime where quantum computers are categorically faster. A regime you can't close with better classical algorithms, but the supremacy result was in such a specialized domain that classical optimization could still keep pace. That's the real story of quantum computing right now. Quantum supremacy exists in toy problems. Real-world advantage remains elusive. Real-world advantage in AI, even more elusive. We have prototype quantum machine learning algorithms. We have simulations showing theoretical speed-up. We have theoretical frameworks suggesting quantum AI could be powerful. But nobody has built a quantum AI system that actually outperforms classical AI on any problem that matters. Nobody. Not one. The closest thing is quantum optimization algorithms applied to small optimization problems. Even then, the speed-up is modest. Maybe 2 to 3 times faster, not exponential. The hype around quantum AI is real, but the evidence is non-existent. Quantum computers exist. Quantum ML algorithms exist on paper, but quantum AI that actually works and actually provides advantage, that's still years away if it's coming at all. And the more optimistic you are about timelines, the more you have to worry about the collision with classical AI advancement. But we're already experimenting. Research teams at various universities have been working on quantum machine learning. They've run algorithms on real quantum hardware. IBM provides cloud access to their quantum computers through their IBM Quantum Experience platform. Anyone can write quantum circuits and run them on real hardware. Researchers have been testing variational quantum algorithms on real systems. These are algorithms where you have a classical computer training a quantum circuit like you'd train a neural network. You have quantum gates whose parameters are adjustable. You run the circuit, measure the output, calculate a loss function, update the parameters using classical optimization, then run again. It's a hybrid approach, and it's been tested on real quantum hardware. The results so far are that for small problems, toy problems essentially, the algorithms work. They can learn to solve simple classification tasks. They can learn simple patterns. But the performance doesn't exceed classical systems and sometimes is worse. The quantum circuit trains slower. It gets stuck in local minima. The parameters don't converge well. The noise from the quantum hardware corrupts the learning. Errors accumulate. The quantum system loses coherence before convergence is achieved. It's not impressive. It's not better. It's just a proof that you can theoretically do machine learning on a quantum computer. On completely artificial problems, on circuits with maybe 10 to 20 qubits, under perfect conditions, you can train it. But we're nowhere near scaling this to real problems. We're nowhere near machine learning systems that use thousands of qubits. We're nowhere near quantum AI that's competitive with classical AI. We're nowhere near the quantum AI apocalypse that people worry about. There's something called barren plateaus that's emerging as a fundamental problem in quantum machine learning. As you increase the number of qubits, the quantum circuits become harder to train. The loss function landscape becomes very flat in most places. The gradients you need to optimize the parameters vanish. It's like you're trying to find a needle in a haystack, but the haystack is so large and so flat that there's no gradient pointing you toward the needle. You're just wandering randomly. It's a fundamental scaling problem. You might be able to train a quantum neural network with 5 qubits, but what about 50 qubits? 500? The barren plateau problem suggests that doesn't scale. Researchers are working on solutions, but it's not clear if they exist. There might be a fundamental barrier to scaling up quantum machine learning using current approaches. And that's where the timeline question becomes critical. Are we going to have practical quantum computers that can run AI algorithms before or after classical AI becomes significantly more capable than humans? That's the crucial race. If practical quantum computers arrive first, maybe we're in trouble. But if classical AI becomes super capable first, We might face that problem with only classical systems to deal with. That's not clearly better, but it's at least a different problem. The most likely scenario is they arrive simultaneously or nearly so, within a few years of each other, both accelerating at the same time. Quantum AI might not provide immediate advantage, but it will provide eventual advantage. It will be pursued by every major AI company and every government with serious AI ambitions. It will be developed in secret by military and intelligence agencies. It will be part of the landscape of advanced AI systems. And it will introduce another layer of uncertainty into an already uncertain situation. We don't know how capable classical AI will become. Will it reach human level, beyond human level? By when? We don't know when practical quantum computers will arrive. Will it be 5 years, 10 years? Never. We don't know what quantum AI can do. Will it be genuinely better or just different? Will the quantum advantage actually materialize, or will classical algorithms keep up? We don't know how to align classical AI. We barely have frameworks for it. We definitely don't know how to align quantum AI. We don't even have frameworks for attempting it. We don't even know if quantum AI will be aligned to the same metrics as classical AI, or if it will find completely different optimization strategies that don't make sense to us. Strategies that are technically optimal but ethically horrifying. We're building the future incrementally with decisions made by different organizations with different goals, all pursuing different directions. And the intersection of all those directions might be beautiful, or might be catastrophic, or might be something we don't have the imagination to predict yet. The uncertainty is the dominant feature of this landscape. Not the knowledge, but the not knowing. The gap between what we need to understand and what we actually understand is enormous, and it keeps getting larger as the technology advances faster than our understanding can keep pace. The problem is that we're dealing with systems that don't follow the neat equations we've written for them. Quantum computers have fundamental physical limits that nobody's rushing to advertise. The laws of thermodynamics don't care what you want to compute. The speed of light doesn't care about your optimization problems. The uncertainty principle doesn't care about your timeline. Start with the fact that quantum computers require isolation. Extreme isolation. The qubits need to exist in a state of quantum coherence, where the system behaves as a pure quantum state, without interference from the environment. But maintaining that coherence is almost impossible. Any interaction with the environment destroys it. Heat, electromagnetic radiation, vibration, stray particles, all of it causes decoherence. The qubits lose their quantum properties, and the computation fails. It's one of the most fundamental challenges in quantum computing. Qubits are inherently fragile. They want to interact with their environment. That's the natural state of matter. And when they do interact, they stop being quantum and start being classical. They lose the superposition, they lose the entanglement, they lose the quantum advantage. The engineering problem is keeping them isolated long enough to do useful computation. But isolation is hard. Every wire connecting to a qubit is a potential source of decoherence. Every photon that bounces off the qubit can destroy its state. Every thermal fluctuation can knock it out of superposition. This is why quantum computers are built in extreme conditions. Temperatures near absolute zero. IBM's quantum computers operate around 15 millikelvin, colder than the vacuum of space. Google's systems operate in similar regimes. You need dilution refrigerators that cost millions of dollars to keep the quantum processor cold enough to function. And even at those temperatures, coherence times are limited. Qubits only maintain quantum superposition for microseconds or milliseconds depending on the qubit type. After that time passes, the quantum state decays. Decoherence kicks in. You lose the computation. That puts a hard limit on the number of operations you can perform. You have a window, typically measured in microseconds, to run your computation and get the answer out before the quantum state falls apart. For simple problems, this is fine. For complex problems, you need more operations than the coherence time allows. You need millions of operations, but you've only got time for thousands. That's a fundamental constraint that no engineering breakthrough can fully overcome. You can improve coherence times. We've gone from nanoseconds to microseconds over the past decade, but the improvement has started to plateau. There are physical limits based on how qubits interact with their environments. You can minimize those interactions, but you can't eliminate them. Not completely, not indefinitely. Then there's the problem of quantum error correction. Qubits are fragile. They make mistakes. A qubit that should be in state A might spontaneously flip to state B, or it might be in a superposition, but measurement gives the wrong answer. These errors are probabilistic. They happen randomly. The error rates are actually pretty high, something like 1% per operation, depending on the qubit type and implementation. 1% might not sound bad until you realize that if you need 1,000,000 operations, 1% error per operation compounds into complete failure. Your final answer is probably wrong. You've got no idea if it's right or not. This isn't speculation. This is what we see in actual quantum hardware. IBM publishes their error rates. Google publishes their error rates. They're all in this ballpark. Some technologies are slightly better, some are worse, but they're all dealing with per-gate error rates that are significant enough to destroy computation if not corrected. And the longer your computation runs, the more gates you execute, the more places for errors to accumulate. A computation that takes microseconds might work. A computation that takes milliseconds probably fails. A computation that takes seconds is almost certainly wrong. Quantum error correction is the tool physicists use to solve this problem. The idea is elegant. You don't use individual qubits. You use multiple physical qubits to encode a single logical qubit. You make the encoding redundant so that errors in individual qubits can be detected and corrected. If a physical qubit flips, the redundancy lets you figure out which one did and correct it without losing the computation. It works, in principle. In practice, quantum error correction requires so many physical qubits to encode a single logical qubit that the overhead is brutal. Estimates vary depending on the qubit technology, but you might need 1,000 physical qubits to create a single reliable logical qubit, a 1,000 to 1 ratio. To build a quantum computer with 1,000,000 logical qubits, you'd need 1,000,000,000 physical qubits. We don't have that. We're nowhere close. Current quantum computers have dozens to a few hundred qubits. We're talking about scaling up by a factor of millions while maintaining control and coherence. The engineering challenges are immense. And here's where it gets worse. Adding more qubits doesn't just scale the problem linearly. The interactions between qubits scale non-linearly. More qubits means more places for errors to happen, more complex error correction codes needed, more overhead, more physical qubits to reach the same logical qubit capacity. It's not clear there's a path to scaling to millions of qubits using current approaches. Maybe new qubit technologies will emerge that overcome these limitations. Maybe there's a fundamentally different architecture that doesn't have these constraints. But right now, every roadmap for large-scale quantum computing runs into the same scaling challenges. The further you try to scale, the harder the engineering becomes. The more qubits you add, the more of your quantum computer is devoted to error correction instinct, of actual computation. You reach a point where most of your qubits are error correction overhead, and only a few are doing useful work. That defeats the purpose. This brings us to the deeper question about quantum computers replacing classical ones. They won't. Not completely. Not even mostly. Quantum computers are specialized machines. They're good at specific problems, simulating quantum systems, factoring large numbers, searching unsorted databases, a few other things. For these problems, they have potential advantage. For everything else, classical computers are better. Writing emails, streaming video, running most software, playing games, browsing the internet, all of that stays on classical computers. Quantum computers don't replace classical computers. They supplement them. They're a new tool in the toolbox for specific applications. Think about it this way. When a specific tool is better at a specific task, you don't throw away all your other tools. You add it to the toolkit. A hammer is great for driving nails. A screwdriver is great for driving screws. You don't get rid of your screwdrivers just because you have a hammer. You have both. Quantum computers are like that. They're great at specific problems. For everything else, classical computers remain superior. And for many problems, classical computers are not just sufficient, they're overwhelmingly better. You don't need quantum computing to browse the web. You don't need it for email. You don't need it for most business applications. For those things, classical computers are cheaper, simpler, more reliable, and perfectly adequate. The actual vision of quantum computing isn't that everyone will have quantum computers in their phones. It's that there will be a few large quantum computers at research centers, universities, and major corporations. They'll be used for specific high-value problems: drug discovery, materials science, optimization problems, financial modeling, cryptanalysis. A handful of applications where the quantum speedup actually materializes and is worth the cost and complexity. Everything else stays classical. You don't need a quantum computer to send an email or watch YouTube. You don't need quantum computing to run most modern software. The reality is much more mundane than the hype suggests. The most realistic scenario is that we'll have a quantum cloud where organizations can submit their problems to shared quantum computers, like how you submit jobs to high-performance computing clusters now. You have a problem that's computationally hard. You send it to a supercomputer center. They run it. They send back the results. Quantum computing might work the same way. You have a drug discovery problem. You send it to a quantum computer. It computes. You get results. It's a service, not something everyone has. It's a utility like cloud computing. Most people never interact with it directly, but it's there for the problems where it helps. That's the realistic vision. Not quantum computers in every home. Not quantum replacing classical, but quantum as a specialized tool for specialized problems. Even for drug discovery, which is one of the most promising applications, the timeline is uncertain. Quantum computers could speed up molecular simulation. Maybe. In theory. In practice, you'd need quantum computers with thousands of logical qubits, error correction implemented, coherence times long enough for the full simulation, all working reliably. We don't have that yet, and we might not for a decade or more. Drug companies are hedging their bets. Some are investing in quantum computing. But they're also improving classical algorithms, using AI to narrow down drug candidates before simulation, using GPU clusters for molecular simulation. Classical approaches keep improving. Quantum advantages keep getting pushed into the future. The drugs you take in 5 years will probably still have been discovered using mostly classical methods, maybe enhanced with quantum-inspired algorithms or hybrid approaches, but not pure quantum computing. This is where the hype cycle becomes important. Quantum computing has been promised and hyped for decades. In the 1980s and 1990s, it was going to revolutionize everything. By 2000, the revolution was 5 years away. By 2010, 5 years away. By 2020, 5 years away. By 2030, probably still 5 years away. The timeline keeps receding. It's like a mirage. Every time you think you're close, you realize the distance is still enormous. Researchers keep finding new obstacles, new limitations, new constraints that weren't appreciated before. The problems are harder than expected. The engineering is harder than expected. The scaling is harder than expected. This happens in technology cycles. It's called the hype cycle or the Gartner cycle. A new technology emerges. Initial results are promising. The hype builds. Everyone's excited. Predictions are wild. We're going to have quantum computers that solve everything. We're going to have quantum AI that's smarter than humans. We're going to revolutionize medicine and finance and energy. Billions of dollars in venture funding pour in. Companies are founded. Stock prices go up. Everyone's excited. Then reality hits. The engineering is harder. The timeline slips. Some of the initial promises turn out to be wrong or exaggerated. The hype peaks. Then comes the disillusionment. People realize the technology isn't as revolutionary as promised. Stock prices crash. Funding dries up. Companies fail. The media narrative flips from excitement to skepticism. This is called the Valley of Disillusionment. It's the low point where the technology seems like it's never going to deliver. Everyone's disappointed. Everyone's skeptical. Journalists write articles about how the technology failed. Academics question whether it was ever going to work. Funding disappears. The field contracts. Then, if the technology actually has potential, something interesting happens. The realistic researchers and companies keep working. They're not chasing the hype anymore. They're solving real problems. They're making incremental progress. The technology actually starts to work for specific applications. Maybe not everything. Maybe not the revolutionary claims. But some things. Real things. Useful things. Slowly, incrementally, the technology climbs out of the valley of disillusionment. It enters what's called the slope of enlightenment. The realistic phase. Nobody's claiming it's going to cure cancer or solve climate change. But people recognize it's useful for specific applications. Stock prices stabilize. Companies are founded on realistic predictions. Funding comes back, but it's more careful, more focused. The technology eventually reaches the plateau of productivity. It's mainstream. It's normal. It's just part of what we do. It's boring. Quantum computing is in the middle of this cycle right now. We're somewhere between the peak of hype and the valley of disillusionment. The initial promises didn't materialize on schedule. Quantum computers aren't solving the world's problems yet. The engineering challenges are becoming clearer. The fundamental physical limits are becoming appreciated. We're starting to see skepticism. Some researchers are questioning whether quantum computing will ever deliver on the big promises. Whether there are applications where quantum computers actually provide useful advantage. Whether the engineering challenges can be overcome. This is healthy. This is what happens when the reality doesn't match the hype. The fear, of course, is that we're going to enter full disillusionment. That quantum computing is going to become the new cold fusion. A technology that was hyped, that turned out to not work, that wasted billions of dollars and then disappeared into obscurity. This happened to nuclear fusion energy. It happened to supersonic passenger aircraft. It happened to domed cities and space colonies, and 100 other technologies that were going to revolutionize everything. Cold fusion in 1989 is the classic example. Scientists announced they'd achieved fusion in a tabletop experiment. Unlimited clean energy was coming. The hype was enormous. The promises were wild. Investors poured money in. Then the experiments didn't replicate. The science turned out to be wrong. The promises evaporated. The field went from front-page news to academic embarrassment. Billions were wasted. The field survived, but in a much diminished form, with much less funding and much lower expectations. Nuclear fusion power generation still hasn't happened decades later, despite continuous promises that it's just around the corner. Sometimes the technology was fundamentally flawed. Sometimes it was just not practical despite being technically possible. Either way, the promises didn't materialize. The hype turned to skepticism. The funding disappeared. The field contracted to a small dedicated group of people still working on it. Will quantum computing follow the same path? It's possible. It's maybe even probable if we keep hitting the same scaling walls and don't find solutions. Could that happen to quantum computing? Yes, absolutely. If fundamental limits we haven't appreciated yet turn out to make scaling impossible. If error rates can't be brought down enough for error correction to work. If coherence times can't be extended far enough. If we're missing some basic physics that makes the whole approach impractical. These are open questions. We don't know the answers yet. There's a non-zero probability that we hit a wall, that we reach the physical limits and can't go further, that quantum computers never scale beyond toy problems, that the promise never materializes. That would be disappointing. Trillions of dollars in investment gone. Decades of research with nothing to show for it. But it's possible. It's one of the scenarios we have to consider. But here's what experts in the field are actually saying when you listen carefully. Not the executives hyping their companies. Not the startups trying to raise money. Not the journalists looking for a dramatic story. But the actual physicists and quantum computing researchers who've been working on this for decades. What they're saying is more nuanced. They're saying quantum computers are going to work for specific applications. They're saying the timeline is uncertain. They're saying the challenges are significant but probably surmountable. They're saying we'll likely see quantum computers with 1,000 logical qubits within 10 to 20 years. They're saying those computers will be useful for drug discovery and materials science and specific optimization problems. They're saying they won't revolutionize everything. They're saying it's not going to happen as fast as the hype suggests, but they're also saying it's probably going to happen. Listen to what they actually say, not what headlines claim they said. Barbara Zhang at UC San Diego, a leading quantum computing researcher, has been clear that the scaling challenges are real. She's also clear that they're probably solvable. She talks about the possibility of quantum computers with thousands of qubits in the next decade. She's not saying it's certain. She's saying it's plausible if we keep making progress. Andrew Childs at the University of Maryland, another leading theorist, points out that quantum algorithms for specific problems do provide genuine speed-up. But he's also emphatic that this isn't universal. Not every problem gets faster on a quantum computer. Many problems get slower because the overhead of quantum computing outweighs the algorithmic speed-up. You need to pick your problems carefully. You need to have problems where the quantum advantage actually exists. Then you need the quantum computers to be built well enough to harness that advantage. That's the realistic view. Scott Aaronson, one of the leading quantum computing theorists, has written extensively about what quantum computers can and can't do. He's skeptical of overhyped claims. He's also clear that for certain problems, quantum computers provide genuine advantages. The challenge is engineering, not fundamental physics. The problems are hard, but solvable. He's been vocal about the distinction between quantum supremacy, which is about one problem designed specifically to show quantum advantage, and quantum advantage, which is about actually useful problems. Supremacy is impressive. Advantage is the harder goal. John Preskill at Caltech, who essentially coined the term quantum supremacy, has also been clear about the timeline. He's saying we're probably 5 to 10 years away from quantum computers that outperform classical systems on useful problems. Not toy problems, real problems. That's a more conservative timeline than the industry hype. That's a more realistic assessment. He's also emphasized the importance of error correction and the difficulty of the engineering challenges. Other leading researchers like Krista Svor at Microsoft and Jay Gambetta at IBM are saying similar things. The technology works. The scaling is hard. The timeline is uncertain, but it's probably happening within the next decade or so. What unites all these expert voices is a common theme: genuine possibility tempered by realistic caution. They believe quantum computers will exist and will be useful. They also believe the path is harder than it looked a decade ago. The challenges are bigger. The engineering is more complex. The timeline is longer. This is the honest assessment from people who have spent decades on this problem. The thing is, none of these experts think quantum computers are going to suddenly become super intelligent or develop consciousness or pose some existential risk through AI. They think quantum computers are going to be useful tools for specific applications. They think most computing is going to stay classical. They think the revolution is going to be more modest than the hype suggests. They think we're going to build quantum computers. We're going to use them for drug discovery and materials science. We're going to make progress on some hard problems. We're going to have useful applications, but we're not going to revolutionize everything overnight. We're not going to create quantum superintelligence. We're going to have a new tool that's useful for some things. That's it. This doesn't mean we should ignore quantum computing. It's still important. It's still worth investing in. It's still worth developing the necessary frameworks for quantum AI alignment, even if we're uncertain about the timeline. It's still worth preparing for the cryptographic transition, but it means we can be a little less panicked. We don't need to assume the worst case is imminent. We don't need to assume quantum computers are going to suddenly appear and destroy encryption overnight. We don't need to assume quantum AI is going to be super intelligent by 2030. These are worst-case scenarios, possible but not probable, not the base case. The preparation, though, matters. We should be transitioning to post-quantum cryptography, not because quantum computers are imminent, but because the cost of being wrong is so high that it's worth the investment to prepare. If we do this and quantum computers never arrive, we've wasted some resources. We've upgraded systems that didn't need upgrading. That's fine. Expensive, but fine. If we don't do this and quantum computers do arrive, we've lost all encrypted communications we sent today, our financial records, our medical data, our state secrets, everything. The asymmetry in the payoff matrix means we should prepare. NIST has set a timeline, transition by 2030 or 2035, depending on the agency. That's enough time. It's not rushing. It's being prudent. We should be developing quantum AI alignment frameworks. Not because we're certain quantum computers will be ready by then, but because it's better to work on these problems now than to scramble when the technology suddenly becomes viable. We should be monitoring the technical progress. We should be supporting the research. We should be thinking about the implications. But we should do this without panicking, without assuming the worst, without abandoning classical AI safety for quantum AI safety. Both matter. Both are important. The resources devoted to quantum AI alignment should be proportional to the probability that quantum AI becomes relevant times the impact if it does. Right now, that probability is maybe 50%, and the timeline is 2 decades. That means we should be spending maybe 5 or 10% of AI safety resources on quantum AI alignment. Not zero, not everything, but a meaningful amount. Enough to make progress. Enough to be ready if the timeline accelerates. The real timeline, if you listen to experts and separate the hype from reality, looks something like this. Quantum computers with 10 to 100 logical qubits are probably 5 to 10 years away with current technology. We might already have a few such systems in research labs. Quantum computers with 1,000 logical qubits are probably 10 to 20 years away. That's when we start seeing applications where the quantum advantage actually becomes useful. Drug discovery, material science, specific optimization problems. Things where the quantum speedup is large enough to matter. Quantum computers with 1 million logical qubits are probably 20 or more years away, assuming we solve all the scaling problems. Maybe never, if we hit fundamental limits we haven't anticipated. We don't know yet if those limits exist. We don't know if they're surmountable. We don't know if there are better approaches we haven't discovered yet. The further you try to scale, the more uncertainty exists. Quantum AI that's actually useful for real-world applications is probably at least as far away as practical quantum computers. Maybe further. You need quantum computers first. Then you need quantum AI algorithms that actually work on them. Then you need those algorithms to provide advantage over classical approaches. Then you need to align them and make them safe. It's not one step, it's many steps, each one taking time. So we're talking a timeline of a decade or more for incremental quantum advantage on specific problems. 2 or more decades for general-purpose quantum computers that could address a wide range of problems. Possibly decades more for quantum AI systems that could compete with or exceed advanced classical AI systems. And that's the optimistic case. That's the case where everything goes well, we don't hit unexpected limits, we solve the scaling problems, error rates come down, coherence times go up. In the realistic case where we hit obstacles and have to work around them, the timeline is probably longer. In the pessimistic case where quantum computing hits fundamental limits that can't be overcome, the timeline is infinite. We might never get beyond a few hundred logical qubits. We might never have practical quantum computers for anything. That timeline overlaps with the timeline for advanced classical AI. If we assume classical AI continues advancing at current rates, we'll probably have human-level or superhuman AI systems in some domains within 10 to 20 years. Faster learning, better pattern recognition, more efficient training, bigger models, better algorithms. All of that is happening now and will continue. By the time quantum AI is a realistic threat, classical AI might already be powerful enough to pose challenges on its own. Or quantum AI and classical AI might develop together, racing to become more capable. Or quantum AI might never become practically useful. All of these are possibilities. The uncertainty remains. The one thing we know for sure is that the future is underdetermined. We're not on a single path. We're on multiple possible paths. Some lead to quantum computers being important. Some lead to them being a footnote. Some lead to them arriving late and being overshadowed by classical AI. Some lead to them never arriving at all. But we don't need to assume the worst case happens fastest. We can prepare for multiple scenarios. We can invest in quantum computing and quantum AI alignment. We can also invest in classical AI safety. We can transition to post-quantum cryptography without rushing. We can monitor technical progress and adjust as more information becomes available. This is not a situation where we need to commit to one scenario and hope we're right. It's a situation where we prepare for multiple possibilities and adjust as reality unfolds. In the end, the story of quantum computing is the story of a technology that's simultaneously more powerful and more limited than the hype suggests. It's a tool with genuine applications and genuine limitations. It's not going to replace classical computers. It's not going to suddenly become super intelligent. It's not going to destroy encryption overnight. But it might help us solve drug discovery problems faster. It might help us optimize complex systems. It might reshape specific industries. It's going to be important for the future. But the future is further away than the hype suggests. The really important thing to understand is that uncertainty is not the same as ignorance. We're uncertain about the timeline because the technical challenges are genuinely difficult, and we don't know all the answers yet. That's different from not having any information. We know roughly what the challenges are. We know what the experts think about the timeline. We know what the physical limits are. We're not in a position of complete ignorance. We're in a position where we have partial information about a complex system and we're trying to make decisions without knowing all the outcomes. That's always the human condition. That's normal. It's not unique to quantum computing. And in the meantime, we have work to do. We have to prepare without panicking. We have to invest without assuming certainty. We have to proceed with caution while maintaining perspective. We have to build the future carefully, knowing that the future is uncertain and the timeline is unclear, but the possibilities are real. We're not on the edge of a quantum AI apocalypse. We're on the edge of a technology that might be genuinely transformative for specific applications. We don't know which way it's going to go yet. The technology might surprise us. It might be more powerful than we expect. It might hit limits we don't see coming. It might take a different form than we imagine. All of these are possibilities. The beauty of this uncertainty is that it leaves room for us to shape the future. We're not locked into a single trajectory. We can make choices about how much to invest, where to focus, what safeguards to put in place, how to prepare. We can adjust our approach as new information comes in. We can course correct if things change. We have agency. We have time. We have the opportunity to get this right if we're careful and thoughtful, and willing to admit what we don't know. That's the real message. Not that quantum computers are coming to destroy everything, not that they're a waste of time, but that we're in an uncertain situation where the best response is to prepare carefully, invest thoughtfully, and remain alert to changes. To be neither arrogant in assuming we know how the future will unfold, nor paralyzed by uncertainty. To do the work that needs doing while staying honest about what we don't know. To build wisdom rather than either blind panic or false confidence. We're not waiting for a quantum AI apocalypse. We're waiting to see what quantum computing actually becomes. And that waiting, that uncertainty, that lack of clarity about the future is exactly where the story gets interesting. Because in that gap between what we know and what we'll discover, that's where the future gets written. Not by the technology, but by the choices we make about how to develop it, how to use it, how to prepare for it, how to align it with our values. That's the real story. Not quantum computers replacing us, but us deciding what quantum computers should be and building toward that future deliberately, carefully, and with both wonder and caution.